Find the area of a regular polygon to the nearest tenth. Um, we developed the formula for this in class. I'm not going to repeat why that's true here. Um, but if you know this formula, it makes it quite simple. The area of a regular polygon equals 1/2 times pa. Our book says AP. I prefer pa. Pa is the length of the perimeter, and A is the length of something called the apothem. The apothem or the apothem is the distance from the center to one of the sides. So I'm going to need to know the length of the apothem here, and I'm also going to need to know the perimeter of this. Well, if this is 5 units long, I know that each side, because this is a regular polygon, each side has to be 10 units long. So I can see that the area, since this is a hexagon, because of 1, 2, 3, 4, 5, 6 sides, I'm sorry, the perimeter will be equal to 60, and that's going to be an important thing that we know. So perimeter will be 60, and these will be centimeters. And we need to figure out the length of the apothem. Well, in any regular polygon, we could figure out this angle. This angle right here is as half of what we defined as a central angle in class. So we know that the entire circle here, if I begin here and go all the way around, there are 360 degrees, and that is cut up into 6 equal angles we call central angles, and they're all equal to 1/6 of that. So if I take the 360 and divide it by 6, of course I get that every one of those angles is 60 degrees, and therefore this small angle right here has to be 30 degrees, half of that. Well, it turns out this is a 30, 60, 90 right triangle. And I don't have to use trigonometry, so I'm not going to. However, I'll talk about what I would do if it wasn't. So in a 30, 60, 90, the hypotenuse we generally call 2x. So my hypotenuse would be 10 here because the short leg is my x. So you can see this is 2x, this would be x, and the apothem is x root 3. So A right here, or apothem, A would equal 5 times the square root of 3. So A equals 5 root 3. Now, if it wasn't a 30, 60, 90, let's go ahead and write the equation down. We know the length of the opposite side, and we're trying to find the adjacent side. So we would use our tangent ratio, and we would write the tangent of 30 is equal to opposite over adjacent. Our variable is in the denominator. Probably a good step to do would be multiply both sides by that variable, so we're not dealing with a variable in our denominator. If I can cancel the a's here, and this becomes 5 over 1. And on this side I have a times the tangent of 30 degrees is equal to 5. These are expressed in degrees. Therefore a is equal to 5 divided by the tangent of 30. And the decimal of this, if I do it on my scientific calculator, 5 divided by the tangent of 30, the decimal value of that should equal exactly 5 times the square root of 3. And I'm going to just compare those two. And yeah, I get 8.666025, etc. For each of these. So this is one way to find the apothem, but in this case, I don't need my scientific calculator because this is because of the special right triangle. Anyway, so then my area would equal right here 1/2 times the perimeter of 60 times 5 root 3. So if I'm rounding this to the nearest tenth, I have 30 times 5 root 3. And of course 30 times 5 is 150, so I have 150 times the square root of 3. And that looks like, to me, 200. The area equals 259 to the nearest tenth, 259.8. And again, since our units were in centimeters, and this is an area, these are square centimeters. Again, why is that, Mr. Roberts? Well, I multiplied a perimeter with centimeters, and the apothem was also expressed in centimeters. So you can see in this formula, I've multiplied centimeters times centimeters, therefore I'm getting square centimeters. This figure is a semicircle, a half of a circle, with a radius of 8 inches. Find the area of the shaded part of the figure to the nearest hundredth. Well, it's a little distorted here on my screen, but if the radius is 8, this would be a radius, and this also would be a radius, and this also would be the radius of 8. So you can see here I have a triangle with a base of 16 and a height of 8, and I have the area of half of a circle. Well, let's write down some of the things that we know, right? The area of a circle is equal to pi times the radius squared, and the area of this triangle is equal to 1/2 times the base times the height. So basically what we're going to do is we're going to take the area of half of a circle. So I'm going to be dividing the area of a full circle in half, and I'm going to subtract from it the area of this triangle. So let's take our half circle first. The half circle would be pi times a radius of 8 squared, and we're going to divide this by 2 because we don't have the full circle, we have a semicircle. So pi times 8 squared over 2. And now we're going to subtract away the triangle, and we subtract this triangular region, we'll be left with just the gray bits here on the side. So the area of this triangle is 1/2 times a base of 16 times a height of 8. And it's asking us to round this to the nearest hundredth. So let me use my scientific calculator and grab a pi here times 64, which is 8 squared. I'm going to divide that by 2. And 1/2 of 16, of course, is 8. So I'll just subtract from that 8 squared minus 8 squared. So I get area of these two regions should equal 36 points to the nearest hundredth, 36.53. And again, they told me that these were in inches, so my area should be in inches squared. And I'm going to conclude with one more problem. Find the area of a regular hexagon. No, this is not a regular hexagon. That'd be ridiculous. This is a pentagon. And unfortunately, I can see this 1, 2, 3, 4, 5 sides. So this is a regular pentagon. This is the radius of this regular pentagon is 3 feet. Again, the radius is the distance from the center of the regular polygon to one of the vertices. So if I could draw a straight line, that would be the radius. This is apparently 3 feet. Basically, if we're going to need to figure out some stuff here, because at the heart of it, there's this little right triangle. If I can find this right triangle, you know, there's 10 of these right triangles. I could just multiply it by 10. Or also, I could remember that the area of any regular polygon is simply 1/2 times the product of the perimeter and the length of the apothem. So I'm going to go ahead and designate that this piece of one of my sides is x, and this we're going to label with a for the apothem. And we're looking at this as like, wait a minute, I've got the hypotenuse and both legs are unknown. How am I going to solve for this? Well, remember again, the central angle up here is there are 5 of them, and again, this is the central angle would be basically this whole thing from the green line to this red line. But if I take 360 and divide by 5, and then take half of that, because that's 72, half of that, I get that this angle right here is a 36-degree angle. Which is really convenient because that's going to, this right triangle is going to allow me to figure out the apothem, and it's also going to allow me to figure out the length of half of a side. If I know the length of a half of a side, I could use that to figure out the entire perimeter. And of course, the apothem is needed here for this formula. So let's go ahead and, I guess, find the apothem first. From the 36-degree angle, I would call this my adjacent leg, and I have the hypotenuse is 3. So when we're dealing with adjacent and hypotenuse, the trig ratio we'll use is the cosine. So I will say the cosine of a 36-degree angle is equal to the adjacent leg in my right triangle divided by the hypotenuse. If I multiply each side by 3, I get that 3 times the cosine of 36 degrees is equal to the length of the apothem, which is great because I needed the length of the apothem, and I now know with great accuracy what it is. So I'm just going to leave it in this form, and when it's time, we'll plug that into our calculator. Let's go ahead and find the perimeter now. Well, half of a side. This will lead to the perimeter. So if this is x, and I've got my 36, and I've got the 3, the side labeled x is the opposite leg. And the trig ratio that deals with the opposite leg and the hypotenuse is the sine ratio. So I'll say the sine of my 36-degree angle is equal to the opposite leg x divided by the hypotenuse. And then if I multiply by 3 on each side, 3 times the sine of 36 degrees is equal to x. And x, of course, is half of one side. So in order to get the full perimeter, I'm going to need 10 x's, if you think about it, right? Because if I need 2 of them for one side, and there are 5 of the sides, so that's 2 x's, 4 x's, 6, 7, 8, 9, 10. So I'll need 10 of these x's. So I now know what the perimeter is also. So the area of this regular polygon is literally equal to 1/2 times 10 of these x's. And I'll just go ahead and write it as 10 times the x's are 3 times the sine, oops, that's funky looking, times the sine of 36 degrees, and then times the length of the apothem, which is 3 times the cosine of 36 degrees. And if you can grab your calculator and evaluate this with me, it looks like I have 1/2 times 10, of course, is 5. Hello, Mr. Roberts. And 5 times 3 is 15. And then I'm going to multiply that 15 times another 3. So I have 15 times 3. I've got 45. I don't know why I'm doing this intermediate step. 45, and then I have sine 36 times the cosine of 36. And let's not forget that these angles are measured in degrees. I hope your calculator is still in degree mode. So we're looking at 45 times sine 36 degrees times cosine 36 degrees. And when I evaluate that, I get the area is equal to, and I'm going to go ahead and round it to the nearest hundredth. So you can look at your screen and practice that as well. To the nearest hundredth, I get that it's 26.41, because I have a 414. So 26.41, and I didn't give units for, oh no, I did, it was feet. So this is 26.41 square feet. So feet, oops, feet squared, or FT squared.